Hey there, awesome physics students. Let's talk about the consequences of Poiseuille's equation for fluid flow in the circulatory system. Just a quick review of Poiseuille's equation. Here, this is telling you about the pressure difference. That is, the fluid flows from high pressure to low pressure. So that's the pressure difference between the two ends of the pipe, or the blood vessel in this case, is equal to the resistance times the flow rate. And in the resistance, we have factors like this blood viscosity, the length of the pipe or the blood vessel, and then we have the radius of the blood vessel here on the bottom. And then again, fluid flow rate is volume per time, the number of liters passing through the system in a second, or something like that. We often refer to this as the resistance term, and then this we often use the letter Q, but that's just the volume flow rate. Okay, so first question here, what would be the effect of having one long blood vessel instead of branches? So in our circulatory system, the blood vessels branch out. Why did evolution choose that for us? Why didn't they just have blood comes out of your aorta and then narrows and then squiggles into a capillary that goes all throughout your body and then comes back to the heart? What would be the disadvantage of doing that? Well, you can probably think of two different ones. One immediately is that if you get a cut, that's your one blood vessel and you're going to bleed a lot. All your blood's going to come out of there. The other thing is, let's look at this equation here. It says that the resistance depends on the length of the blood vessel. And so if the length of the blood vessel is super duper long, then the pressure difference in order to drive fluid through that will be enormous. And so that's a very bad scheme to have one long blood vessel. Instead, they have many parallel branches, and so which are analogous to circuits. Okay. So what's another question we can ask is there an evolutionary advantage for keeping a constant temperature in terms of fluid flow? So we're mammals. Mammals maintain their own body temperature within a narrow range. What's the advantage for doing that? Well, if you recall, we talked about some time ago about how the viscosity will depend on temperature. And so if we can keep a constant temperature, our body can in effect control this viscosity term really well. If we get colder, like a reptile can get colder because they are unable to maintain their own body temperature, then the viscosity of their blood will increase, and that decreases the flow rate, right? So, all right, let's think of another question here. What about the flow rate into and out of your heart? So you have the aorta, which is where blood is coming out of the heart, and then they have the vena cava, which is where blood is coming into the heart. And so the question is the flow rate, Q, volume per second, the same coming into your heart as going out, or is one bigger or smaller than the other? Well, the answer to that, of course, is that they have to be the same. If you have, let's say, 2 gallons a minute coming out of your heart, but only 1.5 gallons per minute coming into your heart, well, what does that mean? That means you're bleeding 0.5 gallon per minute and you're going to die. So you need to do something about that, right? Whatever comes in must go out. And if it doesn't, then where does it go? It has to be accounted for. We can't compress blood or fluids like water, which is the main component of blood. So it has to go somewhere. So the flow in has to be the same as the flow rate out. Okay. Let's think about another question. What would be the effect of high blood fat on the flow of your blood? Think of two effects, two terms in here that will change if you had high blood fat. One of them you would think, hopefully you would recognize, is that the viscosity of your blood with high blood fat, and I'm thinking saturated fats here, though that would tend to increase the viscosity of your blood. And if that increases the viscosity of your blood, that means the resistance term will increase. And if the resistance term increases, and we assume that the pressure doesn't change, then that will decrease the flow rate through your heart. So that's bad. The other effect that could happen is that some of these fats will deposit on the walls of your blood vessels, and that will decrease the radius of those blood vessels. And if that radius of your blood vessels decreases, that will tend to increase, again, the resistance of the blood vessels, which makes it more difficult to get fluids to flow through your system. So that's bad too. And that one especially is bad because of this r to the fourth power. It's very, very sensitive to changes in the size of your blood vessels. Okay, so those are two undesirable effects. Now let's think about the consequences of those for a second. Imagine that you increased the resistance of the blood vessels. Now imagine that you keep the pressure constant. We have to keep one or the other constant here. So what would be if the resistance increases because let's say you have fat deposits on your walls and that decreases the size of your blood vessels. If we hold the pressure constant, what would be the effect on the flow rate? Well, the flow rate is going to go down because if we're going to keep this constant, this increases, then this has to decrease to when these are multiplied together to give the same number. So that seems bad, actually, when the flow rate of blood through your body will just decrease because you've eaten too many steaks. And I'm joking about that. That's not how you get necessarily how you get high blood fat. It's complicated. But anyway, all right. So that's one bad effect. Now let's think again. Let's say again your blood vessel, your resistance goes up, and probably because of the size of you have plaque on the arteries or something like that, that decreases the diameter or the radius of those blood vessels. And this time let's hold the flow rate constant. So imagine that your body does something to keep this flow rate constant. Well, what does that mean here? So you can see what I'm doing here is I'm trying to understand the consequences if I hold one thing constant and then change one thing. You got to do that. Otherwise, it's too hard to make sense of it. Okay, so if I hold this constant, the flow rate constant, and the resistance increases, that means it's hard. The resistance increasing means it's harder for it to flow through there. But if the flow rate stays constant, that means I must be trying harder. So that means the trying is here. That's the pressure difference. That pressure difference comes from your heart, right? The pressure in the aorta is going to be a lot higher than the pressure in the vena cava. And so that's why fluid flows in that one direction. So that means your heart has to work harder. And so the pressure difference has to increase. And that also seems bad. Now, in reality, it's a combination of these two. If your the resistance of your vessels goes up, you get both diminished flow rate and your heart has to work harder. But it's useful to think about these separately so you can understand what's going on here. All right?